chemistry than algebra. That being said, today we're going to have quite a bit of remedial math background because it's foundational. So it's unavoidable to an extent. Hopefully it'll all be reviewed. So we're up to 8. We have 11 enrolled. Let's see who the winners of the last one were. You know that was a competition, did you? I am, as you are probably familiar with, since you guys are Columbia College students, and this is my first time teaching for Columbia College, I am required to take attendance. So I will be doing that on a daily basis. But I will also tell you that outside of that requirement, attendance is not something that I'm exceptionally concerned with. You have to be here, because if you're not here a certain number of days, bad things start to happen. But if you are not going to be here for whatever reason, just let me know, and I can put that into the attendance so that you have an excused absence as opposed to an unexcused one. But I don't really need to know the specifics. I'm not going to ask you for a doctor's note or a birth certificate to prove that you have a child that is ill or anything along those lines. Nor am I technophobic. So if you would like to have technological apparatuses, you are welcome to do so. As I said, I had a friend who recently graduated from here, and she had a few courses where her instructors were very anti-computer. I don't know if that's a campus-wide thing or just certain specific teachers that are just very concerned with those types of things. But from my perspective, as long as it's not disrupting anyone's learning other than your own, I don't care. If it's disrupting your learning, that's your responsibility, right? I don't see why you'd want to pay the money for college and then check Facebook the entire time while you're in class. But if that's what you want to do with your time and your money, as long as you're not keeping someone else from learning, I don't care. Okay? Let's see. Any other snippets before we get officially started? Oh, right. Food and drink. Technically, it's a no-no, right? But this is a 5:30 class. I have a real job too, so I'm not going to be going home to sit with my family for a nice home-cooked 3-course meal before getting here to teach you guys at 5:30. So I'll be grabbing something to eat on the way here, which may or may not be somewhat pressed for time once or twice. So I might have food. I'm not going to be up in the front of the room eating it while I'm trying to talk.
We all agree that smells can be disruptive?
Yes, like, you know.
Like we just make it like a classroom rule, like no steamed broccoli and no yeah.
Don't bring in a jar of sauerkraut, just pop the fresh can right there in the back of the room. Sure, yes. I mean, if we get smoke out of the room, then we can't have a lecture. So, you know, within reason. No food that is so spicy that it seems as if someone has maced the room, right? You know, so, but it's difficult, you know, if you're grabbing something quickly on the way here, it's probably going to be reasonable. If you had time to go to Bangkok Gardens and get the spiciest thing in the world to bring to class, then you probably had time to eat it there. So, you know, okay. All right, well, let's start with who is actually here. Let's see. How do we do this? I suppose that's first name, last name, first name. So Bobby J, over here, right there, okay. Oopsie. Present. How about Christian? Yep, that's what I thought. Elizabeth D. Not yet. How about Kelly A? No.
Oh, yes, that's me. Well, A is my middle name.
Gotcha, Kelly A, yeah. I could probably just say first name since there's probably not a lot of overlap here. How about Megan? No? Ashley? Okay. Amber? that means everybody else should be here then. So, Mary, back there. Christina,
Right here.
okay. McKenya, I assume?
No.
No, back there, okay. Incorrect assumption. And Jennifer?
I am.
That would be Jennifer. There we go. Okay, so we are all here, aside from those three people. I apologize if I didn't do that right. I'm not good with names. I do not have a photo next to your names. There's not that many of you, so by the time of the end of the 8 weeks, I might have your names down. Hi! But I don't guarantee it. What I can virtually guarantee is that if I see you walking around campus in the subsequent semester, that I will recognize your face. I'm good with those. So, you know, you could probably try and pull that finals trick of, do you know my name, and slip it into the middle of the pile. And then I'll just wait until I recognize your face later in a different class and look you up, and then posthumously make sure that you got it. So, may I ask for your name?
Amber?
Amber? Okay. And then we'll take you off of the late list, Amber. We'll see how the other two do. Okay, so my name is Dr. Adam Martin, although that just feels weird to me.
Dr. Martin?
Yeah, you see, Dr. Martin, that like there's Doc Martin, like there's just so many different ways, and none of them really fit. Dr. A is another favorite of mine because I had a Dr. A that was a mentor, so it's kind of one of those like, that'd be kind of cool to slip into that. I don't know, you could also just call me Adam. With a class this small, I'm not going to stick to extremely strict rules about like you must raise your hand type of thing, as long as it's not disruptive, and especially if it's topical, I welcome your questions. So don't need to worry about that so much. I do understand and know that there is a certain degree and air of propriety at Columbia College, and I do not mean to step on that in any way, but as long as you guys can respect my job of being the person in the front of the class supposed to be teaching you guys, you can call me just about anything you want within certain limitations, right? Okay, so I'm gonna get rid of this for now. Turn that on. This is your book. Everybody knows that, right? You all have a copy of it? Yes? Either physical or digital? One of the two? Okay, good. Hopefully I don't have to bring this again, but I might just bring it every time just in case. I have a digital version of it as well. I like to touch things, and smart boards are really sensitive. Everybody gonna fall asleep, right? No? Okay. So that's really small. Y'all guys, everybody knows about Kodac D2L? Yes? Okay. So, if you aren't familiar with that, then talk to me later. I might not be the best person to explain it to you. It's kind of a blind leading the blind system. I'm very familiar with online learning systems. I have not used D2L before, so I'm learning that as we go along. It pretty much, potato potato, works about the same way as most of the other systems that I've used, Blackboard, Canvas, right, things like that. We're going to be using it a lot throughout the course of this 8-week term, so you will need to be familiar with it. Presumably, once you log in to your Kodac, you'll be able to find the class, right? How many guys have checked this already? Handful, good, okay. So we have our opening splash and announcement where you can see things like what class this is and when we'll be meeting, information that you already knew because you knew enough to show up, right? So there is a link to the specific syllabus, which I'm going to click on in a moment, right there. When and where we are meeting, the fact that we're skipping chapter 1, but you should still review it because it's scientific method, very basic math skills, things like scientific notation, basic algebra, things like that. That's my previous question about how long ago it was that we had some math, right? So you should read up on that, but I'm not going to ask you, it's not going to be on the test, aside from the fact that the skills contained therein will be required for the remainder of the semester, right? So do take a look at that. Make sure that you're familiar with it and that you don't have any panic attacks over any information there. If you do, panic attack or otherwise, feel free to talk to me about it. We're going to pick up with chapter 2 today once we're done with the syllabus, and then just kind of barrel through as much of this as we can possibly get done. This is a 3-hour course, right? We're going to last until 8:55 with, let's see how many breaks, I don't know, in the middle of that. I do not expect to actually just talk at you until 8:55. We will have some breaks in the middle of that, getting up, moving around. I'm not a huge fan, or I should say I don't have that many physical activities, so we're not going to like get up and do jumping jacks for every element in the periodic table or anything like that. So we will try and keep this manageable. I don't like it when people fall asleep in my class. I like to think I'm a little bit more entertaining than that, but I do understand that when you turn off the light, that is always a risk. So there we go. I am fairly good at talking. My volume levels might fluctuate throughout the course of the lecture, depending upon how enthused I am about the topic, and or whether or not someone seems to be falling asleep in the back of the room. So I apologize to those of you who are right in front if the volume levels get a little bit high. I will try and mitigate that, considering it is a very small room with closed walls, and therefore I will back up. So let's take a look at that syllabus, shall we? Because that's what everybody does on the first day of class. Such a waste of time. All right, so Chem 109, 3 credit hours, where we're meeting prerequisites, catalog description. There's that math requirement, a little bit of chemistry in the background. Here's our text, once again, which you have all seen. Learning outcomes right there. This is what you should have by the end of the semester, term, whatever. Identify and draw structures. The quizzes and tests are going to be online, so I'm not going to be asking you on an exam to draw a structure. But I do hope that by the end of this you will be able to do so, because doing so will be perhaps required for understanding and answering some of those questions. But I'm not going to be able to test whether or not you appropriately drew the 3-dimensional space fill model of a sugar molecule or something like that. Compare the behavior organic functional groups. Relate chemical principles to biological processes. Those are fun. Osmosis is one of my favorite ones. Describe and contrast proteins, lipids, enzymes, and nucleic acids, the 4 macromolecules that make up all of life as we know it. Predict chemical properties, function groups and active sites. Identify chemical interactions in biological structures and systems. Balance chemical reactions. There's a lot more of that math. Determine energy changes. A lot more of that math. Predict protein or transport properties, osmosis rates, and chemistry of ions and solutions. Hey, even more math. So that's what you'll hopefully be able to do by the time we're done with this. I also realize that how many of you intend and or are required to take any chemistry beyond this course? Interesting. Good. Well then, I will ameliorate some of those concerns. So if you're going to keep going, good. I'm a big fan of chemistry. My PhD is in chemistry. Big fan of biology. My undergraduate and master's degree was in biology. So I like this information. I am motivated about it. I would encourage you to go deeper than this, because as I look at this, and hopefully you will appreciate that my perspective is biased, but as I look at this information, and I'm looking through this book in preparation to teach this course, the first thing that pops through my head is, oh my God, really? But I'm in a very different place than you guys are, right? Like, it should be a situation where I look at the information and think that this is basic, simple, introductory, and everybody should know this, right? But I'm at the end of that journey, and you guys are just getting started along that path. So it's my job to give you the same background and boost that I got in my education that got me where I am now. Hopefully, with a little bit of help, you can go maybe even further in the direction that you want to go, right? So I have taught a lot of introductory courses, so I understand some of the challenges of getting back on the horse, as it were, and picking up some of these basic skills, and which skills are really important moving forward. Some of those things that I take for granted now, but the only reason I can take them for granted is because I had somebody who taught me the right way to do them and made sure I knew what I was doing, right? So, how am I going to test you? We're going to have homework, we're going to have exams. There are two extremes when it comes to how you evaluate progress in a class. One of them is by doing nothing other than tests. I'm the type of person that likes nothing other than tests, because if you tell me what topics are going to be on a test, what chapters that test covers, then I can focus on those chapters, I can focus on the testable elements of those chapters, and I can make sure that I will do very well on that test. And I can do so with a minimum amount of effort outside of the boundaries of the time required for the class. The opposite of that is the type of class that I despise, which is busy work, where the vast majority of the grade is determined by doing things that everyone can do if they just have enough time to do them, and you just have to do a lot of them, and then you have a minimal amount of exams, because not all students do well on exams, right? Different learning styles, different testing styles. Come on in. May I have your name, please?
Elizabeth?
Elizabeth? All right. 1 second, guys. There you are. I'll be nice about it for today, but probably around the 6 o'clock mark, no later than that, I'm going to have to submit this in the future. So I can probably edit it afterwards, but do try and not be too terribly late. That being said, if you are a little bit late, I'm not going to yell at you. I'm not going to tell you don't come in. Just try to not be disruptive when you do come in. Okay? So, here? Yes. I'm going to give you homework. My intention is to have all of that online. I don't know if that's going to work. So there might be some that are not online. I do have a thing in here about how I will attempt to give partial credit for incorrect answers where possible. That's really hard to do with an online homework assignment, right? So depending upon what we're talking about, and if I feel that it is pertinent, I might give you a few assignments that I want you, or a few problems that I want you to do by hand and bring to class with you, okay? I'm not going to spring that on you. You will know about it. So there is that. Exams. There will be 4 exams. The exams are going to make up the majority of your grade. So I do obviously lean closer to the whole exam type of grading than a whole bunch of busy work type of grading. We're going to do some busy work type stuff in lecture. There's lecture notes available online that can help you work through some of the busy work type problems, learning these, applying these things that you're learning in class so that you're ready for them. But the thing is, these exams are going to be online via D2L as well. They're going to open every other week. Every 2 weeks we will have an exam. 8-week course. It's going to go fast. We're going to be covering, if I stay on topic, on average 1 chapter a day. If I'm going to keep up with the way that it's done during the day campus, that's about the speed we have to move. So, we're going to be moving fast. That means that each test is going to be about 4 chapters. I'm going to cut it off per chapter, which means that if I finish a chapter a day, then we should have 4 chapters to cover. If I have not finished a chapter, or if we've gotten a little bit ahead or something, if we're halfway through a chapter, then that chapter won't be on that test. I'm not going to cut a test in half, or a chapter in half for the test. It's either going to be on this test coming up, or it'll be on the one after it. Everybody follow? Okay. So, you will have from the morning of Friday, which probably means sometime around 7:30 to 8 o'clock, because I will activate it the next morning, it will go live, the exams, on D2L. You will have until midnight on Sunday to finish it. At some point during that 3-ish day period, you will need to log on to D2L and take your exam. You will have what I'm estimating currently to be 90 minutes, unless you have documented reason from the university to get more than that. You will have 90 minutes to finish that exam. I'm taking this model of a class from a decade's worth of experience teaching introductory classes at Missouri S&T down in Rolla. 90 minutes, 4 chapters, around 50 questions if I can manage it. Do the math. That leaves you with enough time to look things up if you need to, not enough time to look up everything, right? So coming to class, paying attention, maybe studying a bit, preparing for your test, still highly advisable activities, right? But if it's a question that you know you don't know the answer to, you will have the time to check. What else could you do with an online exam and 3 days worth of time? Come on. I know you already thought of it.
Can you reopen it?
You can't reopen it. Once you, well, you can within that 90-minute window.
You could take it with somebody.
You could take it with somebody. Totally could do that. And I could, like, you know, ask you to sign some sort of thingy that says on your honor you're not going to do that and blah, 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 because it's cheating, and no, it's not. So here's the thing. D2L will cut you off. 90 minutes, 2 hours. It says here 2 hours, which means I have to give you 2 hours because that's the contract, right? So, I'll need to remember that later. Here's the thing. This is my pedagogical opinion, theory, perspective, shall we say. My job is to teach you things, not examine you, test you, and punish you for not knowing things that I already know, that I feel that you should obviously know, because I have some sort of superiority complex. As I said before, if I didn't already have most of this information in my head, I shouldn't be the one up here in the front of the room, right? So that's not fair. The job is to make sure that you guys learn it. And as is stated a little bit further down in the syllabus, my opinion on that is that teaching is one of the best ways to learn. So here's some advice. If you want to get together with some friends to take this test, more power to you. I encourage you to do so. One little caveat. I don't consider it cheating, but you're asking for more work. I still encourage you to do that. Because the test that you get, wow, epic fail. The test that you get will be different, trying not to focus, will be different than the test that you get. So for every chapter, I'm going to have a pool of questions. Hopefully a minimum of 25, better around 50. So that means that if you're looking at 12 questions per chapter, 4 chapters, around 50 questions on a test, if it's a random assignment of which 12 of those 50 questions you see, then that means you are going to be seeing probably 10 different questions than the person you're sitting with. You still only have 2 hours. But what could you do? You have 2 hours to take your test, right? That doesn't have to be the same time as her test. So you could totally get together, both of you take one test, and then both of you take the other person's test. Okay, sure. If you want to do that, go right ahead. Because you're going to get a bunch of different questions. Here's the thing. Why am I doing this? Because you can either let the other person take your test, and that would ethically be cheating. Don't do that. But if you want to get together and help each other take a test, then in order to answer a question, if you say, oh, I think the answer is C, and you know, no, it's not C, it's D, well, then now you're either just playing paper, rock, scissors and, you know, guessing on and hoping somebody's right, or one of you is going to have to explain to the other one why you're right. And that act of synthesizing the information, of taking those snippets of knowledge, those factoids that we list out in class, the act of taking that and putting it together, like putting a puzzle together in front of you, the act of handling that information and organizing it in your own thought process so that the things that are coming out of your mouth are meaningful enough that it can convince the person that you're with that you are correct, that act is called synthesis, otherwise known as teaching. And if that act, telling your friend what answer they should pick and why, is the reason that that little factoid sticks in your head and lasts longer than the time it takes you to flush everything else required for that test, then I feel like I've done my job. So, that's the way examinations will go.
Do you teach any other chemistry classes?
No, not yet. We'll see.
You should keep going up.
I appreciate the vote of confidence less than an hour into our first day of class.
I took it in November and I had to drop it the second day because the guy had like 100 questions of homework. And I'm a mom, so I don't got time
Right,
for that.
yeah, no. No, you should still maybe do 100 questions when you can find the time if it's a subject that you are not familiar with. But yes, doing 100 questions just to prove that you've done 100 questions does no one any good.
Yeah, exactly.
Except for the students who do really, really poorly on an exam. And if that homework is 80% of the class, then at least you know you're going to get a B. Because if you spend enough time doing your homework and making sure that it's right, then there's your grade. Well, that's why I do my tests online.
Oh, there were still tests.
Yes, no, I understand. But that's why I do my tests online. I'm not forcing you to memorize everything. We live in a modern world with access to technology literally on our hips, for most of us, right? With our cell phones and otherwise, laptops and gadgets and doohickeys and gizmos. So, memorizing things, not nearly as useful as knowing where to look for the information that you need, and more importantly, how to apply it. You can memorize every equation that you might need on an exam. If you don't know where to use those equations, you're still going to fail, right? So, that's where I would like you to spend your time. Take the information. Think about how you would ask a question about it if you were me. Maybe find a friend, quiz them about it, and then explain the answer. Because like I said, teaching is the best way to learn. If you have to take the list of facts that I'm going to give you, that I have already given you online in your lecture notes, courtesy of the publisher of the book, don't think I spent that many hours working on those things. That's just a list of facts. And it will do you as much good as any other list of facts. If all you do is read your notes over and over and over again, you will not do well. And you will retain virtually nothing once you're done with this course. And that's not what I want. I want you to hold on to some of this. I don't expect you to hold on to all of it. That's why every class you take, there's a whole bunch of review at the beginning. Because nowadays we don't expect everybody to hold on to things. I'm not that old. I'm not like, back when I was in college, I had a few real old guard teachers. Oh my God. How's this for an example? One of the classes I took when I was in college, a little reminiscing, the study guide was 7 pages, single space, both sided. 7 sheets of paper, so 14 pages. And if you could memorize everything, including the parts that weren't fill in the blank, because on the test, what she did was she took some of those sentences that had fill in the blank sections, filled in the word that was blank in the study guide, and took out a word that was there on the study guide, and the only correct answer for that test was the word that is now missing from the study guide that she handed out. I hated that course. Obviously, I survived it, but I hated that course. So, these are the lessons that I learned about how to not teach. Hopefully, I picked up a few things about how to teach along the way as well. You guys will have to be the judge of that. Anything else? Oh, right. Important, critically important detail that we must discuss and that you must understand and by way of staying in this course agree to. So here's what happens. The test opens on Thursday night. It closes on Sunday night. Friday morning, Sunday night. That's what, 3 days-ish, just shy of 3 days. If you know that there's going to be something that's going to get in the way of that, I have to fly to the moon to spread my grandmother's ashes or something like, if you know something's going to get in the way of that, you should know about it up front, before it happens. Find the time in that 3-day period to take this course, take this exam, okay? That being said, we're all adults here. Life gets in the way sometimes, right? I get it. So, I'm not going to be so draconian as to say that 11:59 the test goes away and suck it, you get a 0. I will give you almost another week before I will tell you that. So, here's what's going to happen. Let's say that you forget. Yeah, life happens. Sometimes you forget. You remember Monday morning, as you're getting the kids ready or heading off to work or whatever. I had a test this weekend, right? Okay. It's going to be there. I will reopen it if I have to. If I can make it right, it'll just carry over, but it'll be there. If you take it on Monday, at any time at 12:01 a.m. on Monday, or at 11:58 p.m. on Monday, whatever grade you get, I will take away 10%. Because you took it late. It's not fair to give you your full grade when everybody else found the time to do it on time, right? If you do that on Tuesday, I will take away 20%. You do it on Wednesday, I will take away 30%. You do it on Thursday, which I should point out is 2 classes later, right? Do it on Thursday, I will take away 40%. If you haven't done it by midnight on Thursday, I'm just going to give you the 0 that you're really, really desiring. Right? So that's the way that works. There is no excuse after that. You just get a 0. And if you've been paying attention when we talk about grades, there's 4 tests and 1 homework that's equal to a test. So what grade are you at if you miss a test? 80%. And that's assuming that you get 100% on everything else. So don't do that. Okay? It's easy for me because technology does most of the work. It's lenient because life gets in the way. It's fair because it's still a little bit of punishment, right? If you have any questions about that, please ask me now. Because I've been doing this for years. My willingness to be a teddy bear and bend over backwards for excuses after almost a full week of time to take a test will be exceptionally low. Okay? Good. Let's see. That being said, Exam 4 will not have that policy. Exam 4 will open right after, the Friday after our last day of class. Okay? It will close on midnight at Sunday. I cannot give you a week if you forget that 4th exam. I have to turn in your grade the following day / Tuesday, right? So there is no makeup window for the 4th exam. That being said, it is not cumulative. It's just the 4th exam over the material that we've covered since the 3rd exam. That being said, this is chemistry. There's no such thing as a non-cumulative chemistry test, right? So, you know, but there aren't going to be questions specifically from chapter 2 on the last test. There will be questions that might involve skills that we learned from chapter 2. Same page? Okay. I'm using the same grading terminology as the person who taught this before me, which in my opinion is exceptionally lenient given the way that my grading works with online exams. But, cool, whatever, I don't care. So here you go, 425 to 500, there's your A. That's, you might note, more than 90%, or more, I should say more than the top 10%. So, I'm not fishing for A's, but come on, guys, it's 4 tests and homework, and it's all online, open book, open note, open friend, open Google, don't use Google. Google will lie to you. Rephrase, Google is not topical, right? There's no context to Google. Surely you can get an A, right? I mean, I'm not trying to punish anybody, but I'm not going to give it away either. Like, you've actually got to take the test, you've got to do the work, right? But there will be 100 homework questions in the first week of course. No.
That's bad. Talking
Different.
is just so boring. You know, you have instructors that are like really good and then really boring and really funny.
Well, I told
And his was just awful.
my neighbor recently finished the nursing program here at Columbia College. When she found out I was going to be teaching there, she was like, good, because my chemistry teacher was real boring. I don't know if I'll be any better, but thanks. We'll see. Okay, so topics we're going to cover on a day-to-day basis. I'm going to try and stick to this as much as possible. Can't guarantee it. We might get behind. I doubt we'll get ahead, maybe. I don't know. We'll see. That's what happens the first time you teach a course, right? First time you use a new book. Blah, 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 blah. Here's all the things we're going to talk about. Library resource. That reminds me. I have some pamphlets, which I'm going to put up here. Free online campus study sessions and tutoring for chemistry. Yes. Use all of the resources at your disposal. That being said, he does know about my online tests. He's probably going to step in for the first few minutes of class on Thursday, introduce himself. He does know about my online exams, so the one thing you won't be able to do is go to the testing center to take your test. But you can go to the testing center to study. You just can't take it there during the tutoring session. Yeah. I'm okay with letting your friends in class help you, but not so much a professional tutor help you. Because that person's not being asked to take this course, right? Like the whole point of turning you guys into co-teachers is because you being the co-teacher is the part where maybe you learn. Taking a tutor and making them the co-teacher, they don't need help with chemistry. So, there's that. Academic integrity, don't cheat. Stuff, withdrawal, incomplete, grade appeal, all that other official stuff. Are we good with that? Can we start talking about, it's not even really chemistry yet, but it's getting there. Okay. Let's talk about something from the book. Any questions about the syllabus before we get started on this? I see a few people pulling out and getting ready. You all see, well, not all of you have gone yet, but Chapter 2 and Chapter 3 are available online on D2L already, right? Some of you have seen them, one or two of you have printed them out. I used to be the type of teacher who was like, I'll give you the notes after I'm done talking about them, but really that was just a pain in my neck because then I had to remember to post them every time, and it really didn't improve anything. So everybody learns differently. If you're the type of person that wants to print them out and bring them, take notes in the margin, cool. If you don't want to print them out, if you want to write everything I say down, I talk fast. Have you noticed? I don't know if that'll work well, but you can do that. However you need to learn, however your note-taking skills work, whatever, I don't care. But here's the thing, you're going to have to be here, but the thing I don't like to see, because I think it's the least useful, is print out your notes or don't, and then come to class and sit there with your arms crossed in the back, just trying to stay awake. You're not thinking about the information. I may as well just be reading off a list of what I need to get from the grocery store tonight. It's going to be just as useful and memorable to you, right? So, whatever you guys need to do, I can't determine your learning style. But because of that, I just decided a long time ago, screw it, and I just give it to you up front. Hopefully I will have your lecture notes available to you well before the day when we're going to cover them. I can't guarantee I will always have that. Like I said, I'm developing this as we go along. So I will try and have, for example, Chapter 4 and 5 for next week available well before next week, so that you can grab them and print them and that you're not like doing that on your way to class, because that's no fun, right? So we're going to keep things based in terms of units of the book. So 2.1, we're going to have our title pages like that. Chapter 2, chemistry and measurements. Really, it's measurements within the boundaries of chemistry, because most of this is just math. It's application of mathematical concepts towards the goal of understanding, and therefore in the future being able to apply it to chemistry. So in chemistry, we take a lot of measurements. We also infer a lot of measurements, right? So we're going to learn about how the difference between inferred, exact, and measured values are as we move forward. So the learning goal of 2.1 out of the book is write the names and abbreviations for the metric and SI units for volume, length, mass, temperature, and time. Those are the 5 characteristics that are going to be most important as we move forward when we talk about chemicals, the properties of chemicals and compounds, the way in which they interact, what forms they take and what forms they change into, and how we measure those things, right? So, measurement is important in chemistry. We have the metric system, which hopefully all of you are familiar with. If you do not live by that, it's fine. We have the International System of Units, or SI units, used throughout the world. There's a lot of overlap with the metric system and the SI system. We use a lot of non-SI things here in the good old US of A. But especially when it comes to things like test questions and exam questions and homework questions, you're going to be doing a lot of conversion to things that are either metric or SI, right? So, point of order, when you're looking at especially exam questions, be very careful about answering the question that you are asked. This is actually a critical test-taking skill in general. Answer the question that is asked, not the question you think was asked. Do you understand the difference? Because especially in a multiple choice question, it'd be easy for me to ask you something like, what's the conversion between this and this, or how many units of this are there in that? And then I can give you numbers. And one of those numbers is going to be in pounds, and one of those numbers is going to be in kilograms. And both of them will be correct, but only one of them will be the right answer for that question on the test, because I asked for the SI unit, not the one we started with. Everybody follow? Metric, SI. For volume, the metric system uses a liter. For SI unit, we use cubic meters. For length, meters and meters, so that's easy. Mass, grams, or kilograms, that's an easy one to mess up, because it's the same terminology, but it's a difference of 1,000-fold. So, like, it's a difference between 1 and 0.001. Very, very different numbers, but they are equivalent. So, that's what I mean by, what am I asking for? Am I asking for the metric answer? Am I asking for an SI answer? Once again, in a multiple choice question, sometimes that will be there to see if you're paying attention. And sometimes it'll just, if I'm not asking specifically for a thing, then look at the answers there. You are only going to see one correct answer if I'm not saying what is the SI unit, what is the metric unit, that type of thing, right? I'm not going to try and screw you up on purpose unless the purpose of the question is, do you know the difference between metric and SI? I'm not trying to screw you guys up, but I do have to have something that tests to see whether or not you're paying attention. Temperature, Celsius versus Kelvin. Time, seconds and seconds. So there we go. So if you want to make a crib sheet, you can, just like if we're comparing things in SI versus metric, time is the same, length is the same. So that makes those two easy, right? And the other ones you just have to be more careful with. Volume. What is volume? I'm going to move through some of this. I'm going to say it quickly. That being said, I can talk about anything for a long time. So maybe quickly, but we all know what volume is, right? But let's just define it. It's the amount of space, three-dimensional space, occupied by something, right? Cubic meters in the SI system, liters in the metric system. So we have some common equivalencies here. 1 liter is volume. Now, when we say a liter, are we talking about gas or liquid?
Yes.
Yes. I like that answer. Thank you. When we're talking about volume, we're talking about volume. It doesn't matter what it is unless I ask you what it is. Because if I said, what is the volume of a certain amount of water, and that's all I tell you, then I'm not giving you enough information to answer that question. Well, water comes in multiple forms. Are we talking about the volume of a certain weight of liquid water, or a volume of a certain weight of gaseous water? Because those are two very different answers. 1 liter is 1.06 quarts. I never understood what a quart is. 946 milliliter is 1 quart. Here we have a graduated cylinder, one common way of measuring volume. We have the 1 liter mark right there. They're telling you that that's 946 mils, or 1 quart. Is that what you would have called that? Right there? 0.946 liters. That's going to come in it's going to be, hey, here's a play on words for a chemistry joke. That's going to be significant later.
Yeah.
Oh my God! Chemistry jokes are just as bad as biology jokes. They're horrible. Hilarious if you're in the right mindset. Length. Meters. Unit of centimeters is common for chemists. Here's some convenient conversions. 1 meter is 100 centimeters. Here's a really, really common one. If you don't have this memorized already, we're not going to use it that much in chemistry, but you're like in life. 2.54 centimeters. 1 inch. Period. End of story. 2.5400000000000000. Exact. Like I said, I don't know how much you're going to use that in this class, but in life, knowing that conversion is just a really convenient thing to have memorized. If you never apply it, then never mind. Flush it. You don't need it. Mass, very different than weight. Something that this book does not spend that much time talking about is pet peeve of mine. So we're going to spend a little bit more time talking about that. The amount of an object, the physical quantification of the material contained within it, that is mass. How is that different than weight? Why did I put not weight?
Because weight is a function of gravity.
Correct, because weight is a function of gravity. If you go to the moon, you will not weigh the same as you do here. You don't even have to go to the moon. If you just go a few miles into the atmosphere, you will not weigh the same as you do here. Technically, if you went to the top of a mountain, you would not weigh exactly, you would need kind of a sensitive scale, but you would not weigh exactly the same as you do at sea level, which is how we define a lot of our weights, is the amount of mass something has at a specific location, i.e. at sea level under one pressure of atmosphere on Earth. At which point, conversion between weight and mass is equivalent. At any other time, your weight depends upon how far away you are from that standard. Whereas your mass does not change relative to how close you are to a gravity well, the most common of which being Earth. That doesn't have a lot to do with chemistry, but it's a pet peeve of mine, so there we go. 1 kilogram is 1,000 grams. 1 kilogram is also 2.2 pounds. Here's the thing. We're going to talk about conversions later, and you can get Google to do these conversions for you. You can ask Google, how much is 1 kilogram in pounds? If you know how to use Google, it'll tell you. You could say, how much is 2.2 pounds in kilograms, and Google will tell you 1. But you can also ask for the conversion between pounds and kilograms from Google, and then you can plug the numbers in wrong. I have a pathologist friend who says that he got a report about a 2,000 kilogram cow. These are from vets. They should know how to do this stuff.
Be a buffalo cow.
No. It was a cow. But I think you did your conversions backwards. Temperature. Measure of how hot, or I'm going to shiver here by way of metaphor, and also because how hot or cold an object feels. The only thing that makes that sentence acceptable for me to say is the fact that feels is at the end of it. Because feels is a subjective, emotional content of how we interact with our environment, and things can certainly feel cold. Here's the thing. We're going to measure in Celsius within chemistry, commonly. We're also going to measure in Kelvin. What's the difference between Celsius and Kelvin? SI unit versus metric unit. And the other difference is where it freezes, or more, yeah, pretty much where it freezes. So here's the thing. Kelvin is an absolute scale. Water freezes at 0 degrees Celsius. It freezes at 273 degrees Kelvin. 273? Yeah, I think so. What's 0 degrees Kelvin? We have another name for it. Anybody know?
Absolute zero.
Absolute zero. That is the temperature at which the electrons orbiting around the nucleus of an atom, that is pertinent to chemistry, in case you didn't know, will have so little energy that they will no longer be able to occupy that orbital space and will fall towards the nucleus. Absolute zero. You cannot get, and I shiver with use of this word, colder than that. Why do I hate the word cold? Because I have taken a thermodynamics course, or 3. There is no such thing as cold. There are simply differences in heat. You guys are well aware of this, right? We're approaching summer, in theory, here in Missouri, right? You walk outside and it's 52 degrees in the morning like it was this morning, and do you go, oh, that's cold? Or do you go, wow, this is so nice? And yet, when we're used to it being 90 degrees, when it gets back to 52 in the fall, what do? I'm cold outside. It's all about how it feels. It's our subjective interpretation of temperature. But temperature is literally just a measure of the average kinetic energy in a molecule. But yeah, if we're going to talk about how something feels, we can talk about how hot or cold it is, sure. Time. What's our standard for time? We're going to actually talk about the standard for volumes here in a little bit. What's our standard for time? Anybody know? I'll give you a hint. It gets smaller and smaller and smaller and more accurate as we get better and better and better atomic clocks. Which is like saying a circle is a round object. Look up round, it says see circle.
Isn't there a nuclear clock in Greenwich Mean and lots of backups?
Yes, but which clock we are using changes. So, and by that I mean it's kind of like, have you ever, when you were a kid, did you have that Mickey Mouse watch, right? But when you grew up, maybe you got a slightly nicer watch. And not just because it had those extra little dials that told you what day of the week it was too, but maybe a little bit more accurate watch. We change which atomic clock we're using based on ones that are more and more and more accurate. So they give us more and more and more decimals in the number of fractions of a second that we can count. We count time based on the oscillations of atoms. And we define a second as a certain number of them. We're not going to get that deep here. We're going to measure in seconds. But it's neat. Look up atomic clock sometime if you want to dive down a rabbit hole on Google sometime. Or Wikipedia for that matter. All right, that's 2.1. Do we need a break? Not yet? Okay. 2.2. Significant figures. Learning goal for this portion, identify a number as measured or exact and determine the number of significant figures in a measured quantity. Why do we have this quantity in a measured quantity? What does this imply? The learning goal stated at the beginning of this section of this chapter is telling you something. What is it telling you? That there are significant figures in measured numbers, but not in exact numbers. Because exact numbers are, by definition, exact. So they don't count towards calculations of significant figures. Problem with that?
No, I very much agree with that.
Okay.
I argued with Cheryl in the last chem course because, yeah.
No, there is an alternative argument to that. They are only exact as we define them. And our ability to define them is limited by our ways in which we measure them, which implies that an exact number is a measured number, and you can go down that rabbit hole until you get to the bottom of a black hole. At some point, you just have to fiat. So yes, an exact thing is exact. There are two balls in this picture. Anybody want to argue with that? Well, I suppose if I want to get really esoteric, I could say, well, what's the real definition of a ball here? Oh my God. So, let's talk about measuring numbers. How long is that stick? This is a centimeter down here, so how long is that stick? 4 what? 4.5. Sure. 4.5. Can we get any more accurate with that than that with this stick? With this measuring stick? No. Because we have only defined lengths upon this stick as single units. So we have 4, we have 5, and we have our best guess is what comes in between. So, here's a slide that's all about what we just did. Estimate the number between, for that final digit, is estimated between the two that we can do. We can't go any deeper than that. You could call this 4.523987. How much of that would you trust? If your life was dependent upon it, how much of that would you trust? Hopefully not much of it. Right? So how can we get more exact? What if we had a few more exact marks on there? Now what is it? 4.5 what? 4.55? Conveniently provided to us if you were reading the slide, right? We're getting more exact because our ability to measure is getting more exact. But the degree to which we can be accurate in that measurement is entirely dependent upon the degree to which we are accurate with our measuring tool. Which is a really bad segue into why eyewitness testimony in law is horrible, and yet it's the thing we trust the most, and it's horrible. I'm not going to spend any more time on that than that. I'm just saying it's another one of those rabbit holes. If you want to go digging, look up why eyewitness testimony is horrible. Corollary. You ever looked at those things where you got to cross your eyes to make something like pop out, right? Or the things where you know it's a square, but it doesn't look like a square, and it looks like it's just flowing to the right? That's your eye communicating with your brain, and your brain going, what the f***? And just breaking and making up. But we trust eyewitness testimony. Because I was there, I saw it. Our ability to interpret the world around us is dependent upon our ability to accurately measure it. And that's as far as we can go. Here, the last digit, the closest we can get, 3.0, right? Would you call that 3.0? You could call that 3.0 if you wanted to, but you couldn't call it 3.05, right? My time measurement is, my measurement of velocity is pretty poor, comparatively, right? Significant figures are how we determine that, how we make sure that we're all on the same page when we're talking about that degree of accuracy with respect to the math that is required for chemistry. It's annoying, but you just got to know it. Or know how to look it up when you're doing the math. One of the two. So, a number is a significant figure if it is or has the following. A number is significant if it is not a zero. So 4.5 grams, how many significant figures? 2, just like it says here in this thing. 122.35 significant figures, all 5 of them, because they're not zeros. A zero that is between two significant numbers is also therefore significant. 205. All 3 of those numbers are significant because we are implying via our Celsius scale here that we can accurately measure at least 1 degree at a time. So 205 is an accurate measurement as more than 204, right? Because we have a yardstick that can tell us that. And by yardstick I mean thermometer, but hopefully you follow the metaphor. A zero at the end of a decimal number. So 50 point is significant because we can measure 1 liter at a time. A coefficient, in the coefficient, if the number is written in scientific notation, so 4.8 times 10 to the 5th, we have 2. 5.70 times 10 to the negative 3. We have 3 significant figures here. Because that number, that 0 right there would not be included if it didn't fall within that value right there. We can measure down to that 0 mark, or we should not include it. Same thing as if this was 200 degrees Celsius. If we knew that we could measure as a point value by point value, then if we had 200 degrees Celsius, it shouldn't just be 200, it should be 200 point. And that tells you that we can measure up to the ones, right? That tells you that you have 3 significant figures there. 50 is a very different thing than 51 or 5, right? A 0 is not significant if it's at the beginning of a decimal number, so 0.0004 only has 1 significant figure. Even though it's really, 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 really small. Did we use a normal, stopwatch, a normal 1 second accurate stopwatch to measure this 0.0004? No, we did not, because it can't get that accurate. but its accuracy is evidently limited to that. 0.075, 2 significant figures. It's also not significant if it's a placeholder in a very large number without a decimal point. 850,000 meters. We don't put a decimal point right there. That implies that we do not have an accurate means of measuring 1 meter at a time. What's the difference between here and the moon? Anybody know? It's like 250,000 kilometers, I think. Could be wrong about that. Hey, Google.
Okay, Google. Okay, Google.
I love having computers in the
Okay,
classroom.
Google.
You figure that out for a second and get back to me. So, when we get that number, how many significant figures are going to be in it? What's the difference between here and the moon? For one thing, I'm going to guarantee you it's going to be an average. But the accuracy of that measurement will be limited by the means in which we measure it. What's the answer?
238,900 miles.
Miles. There we go.
Uh,
A little bit different. So how many? 238,900 miles. If we wrote that out, I can guarantee you that there's 2 zeros there that aren't significant, right? Because they're at the end of a measurement that does not have a decimal point. Unless, of course, we get into Wikipedia and it gives us a decimal point. If it did, I would go into Wikipedia and edit it to get rid of it, because that's a lie, because it's an average. Because the moon does not always have the exact same distance between the Earth and us. It gets a little further away, it gets a little closer. That's the way elliptical orbits work, but this is chemistry, not astrophysics. So we won't spend more time on that. So, all non-zero numbers in a measured number are significant by definition. 38.15. 5.6 has 2. 65.6 has 3. 122.55 has 5. 122.55, 0, 0, 0, 0, 0, 0, 0, 0, 0. If we're just throwing a whole bunch of zeros in there, if you have an accurate way of measuring it, yes. If we don't, then you're just throwing zeros on there to lie to me. Don't be a liar. This is why we need to have agreed upon rules for significant figures. So the Ruskies doing math aren't completely screwing up our math because they're just throwing 5 zeros on to laugh at Americans. Or to claim that they're more accurate than us. Which by no means implies that Russians are doing anything wrong. They're just an easy group to pick on right now. For no particular reason. A phrase that my 4-year-old son likes to say for some reason. I don't know where he gets it. For no particular reason. Why did you grab that spoon? No particular reason. Where did you get that from? What TV show or Google thingy? Never mind. Zeros between digits, between non-zero digits are significant. We already have these rules, right? We're just reviewing them on different slides again. 50.08, how many? 4. 201, 3. 0.0702 pounds. Zeros between significant digits are significant. 7 is significant. 2 is significant. So that one right there is. But that one right there, it's a placeholder after the decimal, so it's not significant, right? That's why this number right here on the right is 3 and not 4. Same deal for these 2 zeros here. They are between significant numbers, so they are significant. Zeros at the end of decimals are significant. This is why if you see 40.00, this is true on an exam question as well. If you see a number like this, 40.00, that is telling you that I can measure that number accurately. And therefore those zeros are significant. That is why on that yardstick, when we had to guess 4.5, we should not guess 4.5139682. Because we're just making it up at that point, right? We're guessing at the 5, 4.5, 3.5, whatever it was. Anything past that, we're just making it up.
Can't we only be as accurate as the markings?
As the markings? Yeah.
So 4 or 5, the only significant figure would be 1.
No, Because we can assume accuracy within the estimated value at one point past it. So that 3 and 4, we can say 3.5.
Okay.
But we can't say 3.55. Now you break that down, you give me 10 more slices in between, accurate exact measurements. Now I can say 4.55, but I can't say 4.559. Unless, of course, you give me a ruler that breaks that last millimeter down and gives me 10 more hashtags. Then I can. So if I give you a 40.00, that's telling you that those are exact measurements. Everybody follow? Significant figures are annoying. But understanding what they are in the rules is important so that you can accurately perform these calculations. The 1 0 that you can always throw out is the 0 that lets you know it's less than 1. 0 point, I don't care what it is. That first 0, 0 point something, never significant. Out of curiosity, who can tell me what that would be in scientific notation? 0.003.
3 to the negative 10.
3 times 10 to the negative
10 to the negative 3.
3. If I wrote it like that, would that make it easier to see why there's only one significant digit there? 3 times 10 to the negative 3. How many significant digits? Just 1. Because it has a value of 3 on our arbitrary measurement of whatever unit we're using, right? 1. That's why this only has 1. Now, if it was 0.0030002, that would be 3.0002 times 10 to the negative 3. How many significant figures then? More than 1. I don't remember how many zeros I threw in there. 5? Thank you. I was making that up. But still, it illustrates the point, right? This is boring chemistry. But it's necessary chemistry. Zeros used as placeholders? Not. 2 significant figures in 44,000 kilometers and 810 centimeters, or 6,150,000 grams. Getting ahead of ourselves, how many kilograms is that? I'll give you a hint. How many kilograms is that?
6,150.
Yeah. If you don't see it yet, don't worry, we'll get there in this chapter. Zeros, where we're writing them out, this 0 right here, because it is written out in scientific notation, we're not talking about this 3. We're talking about that 0. Because it is written out, that tells you that this measurement was made with a degree of accuracy that makes that 0 just as real as a 1 or a 2. When you're converting a number to scientific notation, one of those skills that was back in chapter 1 that I'm just assuming everybody has, right? When we're converting a number to scientific notation, those numbers right there, they get lost. We don't keep them. 3.0 times 10 to the negative 1. But we have 30 here because it's written out. So how many significant figures do we have? 2. Why? Because this isn't 0.3 centimeters, it's 0.30 centimeters. That last 0 is significant because we could accurately measure it. But all of these zeros in 400,000, gone. What would change that? One tiny little thing would change that. What would it be? Decimal point. Could change that. That just sounds like it's almost sneaky, doesn't it? Almost like an "are you paying attention" type of sneaky. Like an answer the question that was asked type of sneaky. Like explain to your friend why it is or is not significant type of sneaky. Exact numbers do not have significant numbers. They do not affect our calculations for significant numbers because they are whatever they are. Definite, defined, 2 baseballs, 8 cookies, unless you're arguing with my son and he'll tell you that one of them is broken and it doesn't count, so there's only 7 cookies. I don't know what the 2 half cookies are, but they're not cookies. This is a thing about object permanence that I don't understand because I'm already past that developmental stage and it's impossible to argue with a 4-year-old. So, 8 cookies, 2 baseballs. Another exact number are certain but not. Here's an important little caveat. Put a little gold star next to this. Most, but not all equivalencies, because it depends on how we're getting them. If it's a defined equivalency, then yes, they're exact. 1 foot is 12 inches. Now that defined equivalency can get kind of screwy later, because we could do things like 150 milligrams per pill. That's an exact equivalency in this specific example that we're talking about. Because we're assuming that each pill has exactly 150 milligrams. Because that's the way our medical terminology and the way our medical system works. That's one of the reasons why certain drugs are FDA regulated and approved. It's one of the reasons why over-the-counter supplements are not FDA regulated, and just like what you're going to get depends. It's one of the reasons why people are ODing on heroin. You might think that you're good at regulating your own personal habit, but you don't know what's in that thing that you're injecting into your blood. And if there's even a little bit of fentanyl in it, congratulations, you are on a fast track to OD, and that's a fast track to a very long nap. And a painful ride to get there. We don't know how much of the active ingredient, if there even is an active ingredient, is in some of the over-the-counter and herbal supplements that we're taking. It's one of the reasons why we have this pain in the process of getting FDA approval, or at least some means of making sure that when I say I have this much of a thing, it's that much of a thing. And when it comes to people who are interested in being nurses, this is particularly apropos, right? Exact numbers are not measured as much as they may be counted. They do not have a limit, but they also do not affect how many cookies can there be in the world. Oh, once again, we have to ask what's a cookie. Do the Keebler things count? Do we count snickerdoodles as cookies, or do they get their own category? I mean, we're kind of splitting horses. Horses, hairs, splitting hairs, both. Defined equivalencies, these things are considered exact, which means you can use them in math. This is the important take-home here. Exact equivalencies can be used in calculations without affecting significant figures. If I know that I have exactly 1 meter, 1.0 meters, how many significant figures do I have? Two. 1.0. I gave you a 0 there, right? I didn't just say 1. 1.0. How many centimeters do I have? One meter is 100 centimeters. So how many centimeters do I have? 100. Do we want to get snazzy and say 0.0?
Do you have to?
The number of significant figures in this is not affected.
Okay.
So, no. But we know we have 100. Significant figures can be annoying. But you have to understand. You have to be able to apply them at least as far as being able to do the calculations that you're presented with on, say, a homework problem or an exam problem. on the subject of calculations, let's see, we've been going for just over an hour. Want to take a break? Let's take a break. We're up to 2.3. I think we got to get to 2.6, and we have plenty of time. So, it's quarter till. Make sure you're back here by 5 till, but if everybody's back by 10 till, then we'll get going. But go to the bathroom, get a drink, stretch your legs, do something. Can's that big around, it's that tall, but it's just a tin can. Like you open it with the same can opener that you open a can of green beans. I say that, and almost all green beans now are like pop-top things. So you gotta cut it open, lid pops up. So I did that, poured it out into the thing that I was putting my wine together, rinsed it out, sat it in the sink, and then I was rinsing my hands. And then I have this thing when I'm rinsing my hands, when you're making things like that, you don't want to dry them because you're touching things, you're contaminating your hands again because nothing in your kitchen is sterile, nothing. And so I went to flick my hands to dry them, right next to the sink. You know the thing about really thin sheets of metal?
Oh,
They're sharp.
and those cuts hurt so much.
Flicked right past, and I got a cut that starts here, through that finger, and my fingers were lined up like this when they flicked past. So it sliced whoosh, through all 3 fingers, almost all the way to the bone. I was like, I think we should go get some stitches. Just kind of like holding it together, like, this is gonna hurt later. Because that's the other thing about tin cans, when you're moving your hands fast, they're sharp. So I had a really nice, deep, sharp cut that I couldn't feel until about 20 minutes later. Then I felt it. All right, let me go get that light off. Anybody have any other questions about what we've been talking about so far? Are we on the same page? I think this is what I mean by like, I'm not sure how fast I'm gonna move. I think we're on track. I think. All right, rounding. Do we need to learn about rounding? Hopefully not. Rounding rules. If it's 4 or less, it goes down. If it's 5 or greater, it goes up. Right? Well, I'm good with this, right? Okay.
Especially
So-
with grades.
What's that?
Especially with grades.
That's the nice thing about points. I don't have to worry about rounding. 425 points. 424? No. 425? Yes. Okay. 8.4234. How many significant figures is that?
5.
5. We have 5 numbers. None of them are 0. Therefore, all of them are significant, right? So, if we round to 3 significant figures, then we're looking at the first 3. So what's the 4th one? It's a 3. So we round down, we get 8.42, and we drop the 3 and the 4. If we go to 2 significant figures, same thing. We keep the 8, the first 2, and then we look at the next one, and that's where we change, right? So if we're looking at 2, 8.4, the next one after that is a 2, so we round down. So if we're rounding off to 8 point, why is this important? It's rounding rules. We all know this, right? Why do we need to worry about this? We know that we have 5 significant figures here. Why would we need to round to only 2?
Because another figure in our operation has only 2 significant numbers.
Exactly. And now that he said that, you might recall me mentioning something exactly like that earlier, right? If we're having to do math where we're working with 2 numbers that both have significance, we can only be as accurate as our least accurate measurement. So it doesn't matter if we knew that we had 8.4234. If we're multiplying it by a number that only has 2 significant figures, say 2.1, the answer has to be rounded down to 2 significant figures. 14.78, rounded to 3, 14.7, the next one's an 8, so it goes up. If we're rounding to only 2, it goes up to 15. Because 14, 7's higher than 5, equal to or greater than 5, so it goes up, there we go. Here's an interesting one. 3,256, round to 3 significant figures. It gives you the answer here, but when I first asked that question, does that make your brain go, what, for just a half second? It's easy for us to look at 8.42 and say round to 3 significant figures for some reason. At least it is for me. But when you look at a number that's bigger than that, that's bigger than a decimal, and you say round to certain, like, why would you ever do, like, same reason. We're limited by our most accurate, or I should say least accurate measurement. Round this to 3 significant figures, we get 3,260. Yes?
If it was 3,254, would it be?
3,250. Yeah, we round down. Rounding works exactly the same way every time. It just, where do you cut it off? The next number, is that fiber up? Goes up. If it's 4 down, goes down. Or I should say, stays the same. Because it doesn't actually go down, it just stays the same, right? 3,256 rounded to 2 significant figures becomes 3,300. And for some reason that makes me cringe. Like, no, you can't say that 3,256 is the same thing as 3,300. Those are really different numbers. Yeah, but only because I can appreciate that 3,000 is a big number. Like, I try and picture 3,000 baseballs or 3,000 cookies, and that's like, it's hard for me to picture 3,000 cookies. But I can mentally, if I had $3,000, think about it that way. If somebody was like, if somebody said, you owe me $3,256, but let's just round to 2 significant figures and make it 3,300. You'd be like, I'm not giving you $44 more than I need to. You're crazy. But here's the thing, that number back here, just because it's tiny doesn't mean that it's not significant. We round the 8.4234 to 8.4, we're losing 234 10,000ths. That's a lot if the thing we're looking at can be measured that small, right? So economy of scale kind of applies here, but the math works exactly the same, whether we like it or not. Every time I look at something like, ew. All right. When we multiply or divide, the final answer is going to always have the same number of significant figures as the one having the fewest. We can only be as accurate as our weakest link. We all remember order of operations, right? I hate those memes on Facebook, and yet every time they happen, like I look at it like, oh, okay, you know what I'm talking about? Like, a sock equals 10, and a hamburger equals 5, and a soda cup equals 1, and then it gives you some sort of a mathematical operation, and then it's blah, blah, blah. And then, of course, there's that teaser, only the top whatever number percent of people can answer this correctly. And then at first I'm like, okay, I know what that is. Do the math, because it's an interesting little algebra problem. Do it really quickly, and then I'm fine. I don't have to post something until I look at the answers, and like the first 20 are wrong. I'm like, oh my God, I'm so sad for the state of education in the country. And then I feel like I really have to answer. No! Resist the clickbait. It's so hard. Here's the calculated number. 2.8 times 67.40 divided by 34.8. That's the answer. 5.422988506. You can probably keep going. I bet that's just the limit of the calculator. I haven't actually plugged this into a calculator. It probably keeps going. It's like pi. Probably not like pi. Pi never ends. That number probably ends somewhere. I doubt it ends right there. But we are limited to 2 significant figures because that's the least accurate thing we have in our multiplication. So what's the answer? 5.4. Even though we could go much deeper than that. Our accuracy in our answer is limited by our accuracy in our measurement. You all heard the phrase, let's be politically correct. Crap in, crap out. Are you familiar with that phrase?
Garbage in, garbage out.
There we go. Garbage in, garbage out. That works too. There's a much more colorful version of that, which I should probably not say. So, Here we have another interesting thing. If you divide 8 by 2, the answer is 4. And if you were only dividing 8 by 2, then the answer would be 4. But we're not dividing 8 by 2, are we? We're dividing 8.00, which implies, since it's a number given to you, that we are accurate out to 3 significant figures here, right? Divided by 2.00, so the answer is not 4, it is 4.00. If this was 8.00 divided by 2, what would the answer be? 4. Why? How many significant figures does 2 have?
1.
Just 1. Addition and subtraction, 2.012, 61.09, 3.1. These are, economy of scale here is huge. We're dealing with 2 with a really small number, 3, and 61, which is relatively a large number, right? We add all of that up together, but we have to round to how many significant figures? We're looking at accuracy here. Our accuracy within our decimal places is down to what? Tenths place. Fewest decimal places. Yes, we measured this out to 0.012, but that measurement was only measured to the tenths place. So what's the most accurate answer we can get in this addition? Limited by the tenths. It might be 3.01. It might be 3.07. It might be 3.0000000000001. But we don't know because we could only measure it to the tenths. So that's as far as we can go. Subtract, same thing. We've measured out to the hundredths, but our smallest one is the tenths decimal. So what do we have to do? Round to the tenths. We can round up, that's fine. So there's a difference between being mathematically accurate. What's the mathematically accurate answer to this question? 66.102. Everything in there, right? But when it comes to our ability to do this math with respect to chemistry, chemical equations, and evaluations, we have to take into account our degree of accuracy. That's where significant figures comes in. That's why we would have to round it off at 61.1. That's why we would have to round it off at 62.1. In this case. So that's 2.3. That, for the most part, leaves discussion of significant figures behind because it's got all the rules and it applies all the rules, right? It applies it multiplication, division, addition, and subtraction. We're not doing calculus with significant figures here. So, probably about as far as we need to go, right? Prefixes, inequalities. The prefixes are just things you need to learn or look up. It's the equalities that are the part that we're going to spend a little bit of time on. Using numerical values of prefixes to write a metric equality. A kilometer is a prefix to the metric and SI unit of meter, right? So, 1,000 meters. What does kilo mean? Kilo means 1,000. 1 millimeter is equal to 0.001 meters. Milli also means 1,000. Did you catch that spittle at the end? What's the difference between a kilometer and a meter? It's a 1,000-fold difference. What's the difference between a meter and a millimeter? A 1,000-fold difference. In the same direction, going from bigger to smaller. The difference is a kilometer is 1,000 meters. A millimeter is 1/1,000. That's the spittle at the end, right? Of a meter. It is a fraction of a meter instead of a I shouldn't even say instead of a multiplier, because it's still a multiplier of a number smaller than 1, so that, like, I don't know. Depends on how you look at it. Y'all are familiar with kilometers, right? It's that thing on your odometer that you never actually look at. You may not be familiar with millimeters. Probably are, because most inches, like inch rulers still have that metric side of them, most of them. I can't believe that. Like I went to Walmart and I bought a yard, like a foot stick, measuring stick. And it wasn't until I got home I realized it was only in foot. It's like only American unit. There's no metric on there. I was like flipped it over. What the? It's fine for my 4th grade daughter. Just annoyed the piss out of me. A prefix around an otherwise agreed upon unit means that it is a multiplier. See, there's that word again, a multiplier of. That multiplier can be larger than 1 or smaller than 1. That's why I tripped over it earlier when I first introduced it to you. So we have a kilometer is 1,000 meters, but a millimeter is 1/1000th of a meter. It's still a multiplier, it's just that the multiplier is less than 1, right? It means that it is a value of that unit of some other average denomination. A kiloliter is the same thing as a kilometer, at least with respect to its multiplier. What is the multiplier for kilo? 1,000. How would you represent 1,000 in scientific notation? 10 to the 3? How would you represent a millisomething in scientific notation? 10 to the -3. Still 1,000 either way, right? Now this is easy at first. Like here's that kilograms, right? 1,000 grams. Tera is 10 to the 12th, giga, mega, kilo. So a kilo is 1,000 meters. A megameter. That's just stupid. A megameter is 1,000,000 meters. Where have you heard that abbreviation used much more colloquially?
Megaton.
Megaton, perhaps? You've probably heard, probably heard it much more commonly megabytes. Although nowadays you may not even be familiar with that. Other than megapixel, that's common enough still. Megapixel, like you can't buy. Seriously, I tried to buy a little jump drive. I was like, oh, I don't need a very big jump drive. I had something I wanted to transfer to for a friend. I'll put it on a jump drive. Tried to buy a jump drive. I could not find one smaller than 4 gigs. They weren't for sale. I checked all over town. Well, all over. I checked 4 places. We're going to call that all over town. Round up. Should I have gone to 5 to round up? No, that's fine. Megabytes. Mega's 1,000,000. 10 to the 6th. Gigabytes. 10 to the 9th. Terabytes. 10 to the 12th. We're measuring hard drives in giga and tera right now, right? How many of you guys have a terabyte hard drive in your computer at home?
Oh, I think this one is.
I have 3 1 terabyte hard drives. That's really not that impressive. When we start measuring solid state drives in multiple digits of terabytes, that's when it'll be impressive. But then we'll have non-solid state drives. And so can you get bigger than can you, I don't even know, I think petabyte comes up to share.
Oh, yeah.
Can you do a petabyte
Oh, yeah.
drive as a disk? Wouldn't that half the almost be?
In a
Because I mean,
server.
they're just like SATAing multiple terabyte drives to get that, aren't they?
In a server, but they're usually in a layered RAID.
Yeah, exactly. So cheap, but whatever. This isn't computer. This is chemistry, supposedly. We'll take little trips, tangents every now and then. All right. So we're familiar with milli, abbreviated with a lowercase m, as opposed to mega, which is abbreviated with a capital M, right? We're familiar with millimeters, milliliters, right? We're probably familiar with centimeters. Are you familiar with centiliters? What would a centiliter be?
CC? That's right.
A cc is a milliliter. A cc is a cubic centimeter, which is the definition of a milliliter. We're going to get to that in a minute. A decaliter, a centiliter, is a tenth, or excuse me, yeah, a tenth or a hundredth of a liter. So a centiliter would be how many milliliters? What's it take to go from -2 to -3? An order, a factor of 10, right? 1 to go from 2 to 3, right? But we're 10 to the whatever. So a centiliter would be 10 milliliters. If that feels weird, if you're like, wait, is that I never really, it's like, okay, what's 10 millimeters?
Centimeter.
Centimeter? It all works the same way. I will be very surprised if you ever actually, I can guarantee you that there will be times when you will refer to decaliters. As a nurse, or as a chemist who deals in volume, you will refer to decaliters. I'm not exactly working in an avid chemistry lab, so I don't know if you'll ever refer to centiliters, but there are some times that you will see two terminologies in terms of decaliters, which is just weird, but okay. That's the way it works. Question?
Pet peeve, the
Decimate?
the misuse of decimate.
Decimate?
Yeah, they use it all the time. As what they mean to say is annihilate. Decimate means 1 in 10 was destroyed, removed, whatever.
Oh, nice. As opposed to annihilate, where everything is gone. Interesting. Which is very different than disintegrate, which is 8d10. That's like, never mind. So, milli, micro, nano, pico. We're just getting smaller. This is still a multiplier, guys. This is a multiplier just as much as these numbers are, right? It's just a multiplier that's less than 1. Smaller than 1. By the way, how many significant figures in this number? 1. How is that a trick question?
Oh no.
Because these are exact equivalencies, and how many significant figures are there in exact equivalencies? They don't have significant figures. But if I asked you how many significant figures in 0.000000001, it would be 1. Everybody follow? Did I confuse anybody there? I'm not going to put literal trick questions on your exams or on your grant quizzes, but I do like to point them out. All right, daily values for selected nutrients. Why are these terms interesting? Why are they important? It's beyond simply being able to measure the appropriate amount of a drug to put into a pill or otherwise, right? It's also important for your ability to interact with your diet and your intake, your metabolic requirements on a day-to-day basis. Because when you look at the side of this Powerade, it tells me how many calories are here. What's a calorie?
It's 1,000.
Well, in this case, it's a kilocalorie, yes, but we'll get to that later. A calorie is a unit of measurement for which category?
Temperature.
Temperature or energy, right? We also have fat in grams, sodium in milligrams, potassium in milligrams, carbohydrates in grams, protein in grams, and then we break down into the micronutrients where they just give me a percentage value of my daily intake. 4 of these and I'd be completely good on my niacin intake for the day, assuming that I was an average male of average weight of average activity, which we will also talk about a little bit later. 800 milligrams of phosphorus sounds like a lot. It's not. It's a milligram, right? That's less than a gram. That being said, a gram of phosphorus is not equivalent to a gram of sugar. It sort of is by weight, right? Or I should say by mass. But when you look at it, it's not going to be the same. Why not? Can you get ahead of the lectures and tell me why?
Different density.
Different densities. It is amazing to me, working in the lab, I can measure out 40 milligrams of one substance, and there's this, I'm going to say huge amount, but please realize in the biochemistry lab I work in, a huge amount is something that could still fit on the tip of my finger. But I'm talking about, like, there are some chemicals I measure out on a millimeter scale, and I'm talking about a few grains of this stuff, and I'm done. And other things where it looks like I'm trying to make a sugar cube worth of this stuff, and it's still only 40 milligrams. That's density. We'll get to that later. But by mass, a gram is a gram, right? Question?
We'll just like a statement or something. There's a video on YouTube where somebody asked, like, what's heavier, a pound of bricks or a pound of feathers?
Right.
Yeah, and that just reminded me of that.
Right. What's bigger, a pound of bricks or a pound of feathers?
Yeah.
You want to measure volume, but yeah, it's a pound is a measurement of weight. So what's heavier? They're equivalent, right? But a lot of people are going to just jump.
Bricks. Yeah, they're gonna jump to bricks.
Yeah, because the brick is heavier than the feather. Well, certainly. An equality shows the relationship between two units that measure the otherwise same quantity. That's what the equal signs mean. They are equal. 1 meter is 100 centimeters. They are equal. 1 meter is 1,000 millimeters. They are equal. We're going to represent that in a different mathematical way. Actually, let's do it here. Here we have an equivalency. 1 meter equals 100 centimeters. Somebody do something that involves algebra and give me that exact same equation, except involving 3 numbers instead of 2. Here's where I wish I had the Jeopardy theme song on an easy button, just to give us a soundtrack to that uncomfortable silence. So what would happen if I took these two sides? Is this an equation? 1 meter equals 100 centimeters. Is that an equation?
Yes.
There's an equal sign, right? So yes, it's an equation. So according to our basic understanding of algebra, what can I do to an equation? Anything I freaking want to, as long as I do what? Do it to both sides. So I'm going to divide both sides of this equation by 100 centimeters. What does that give me? 1 meter over 100 centimeters equals, what's 100 centimeters divided by 100 centimeters? 1. So, that's an equivalency. 1 meter over 100 centimeters. You divide those two very different numbers. At least they look like very different numbers, right? But they are both equal to each other. So you divide those two things together, and what are you going to get? 1. If I take 1 apple and divide it by 1 apple, I get, metaphorically, 1 apple, because you can't actually divide an apple by an apple. It doesn't work that way. But we're going to come back to that pretty quick. But that's what they mean by equivalencies and why they're important in math, in numbers. Equivalencies: 1 meter, 10 decimeters, 100 centimeters, 1,000 millimeters. These are all exactly the same thing. They are all names of exactly the same length. And because I'm using the word exact here, that means that they are exact equivalencies. Which means that they do not have significant figures, which means when we use them in our math, they do not affect our significant figures. When we talk about using volumes in health sciences, we don't usually talk about liters. What's this? You know? I'm bad at estimating volumes. This is probably more than 1 liter. Might be like 1.5 liters.
Mm-hmm. I think those are usually 2 quarts.
Which now that we had those things earlier, we could figure out what that volume was, right? This is 1.25 pints or 591 milliliters. So this is just over half of a liter. This bottle of Powerade that I have here from the vending machine just outside the door. As a nurse, or anyone involved in the medical field dealing directly with patients, how often are you going to work with volumes greater than a liter, greater than twice the size of this bottle?
All the time.
Per patient? In one bag?
Well, I mean, if you're dealing with how many, how much urine's in their bladder, if you're scanning
Okay, there you
them,
go.
all that kind of, if you're measuring
How much blood you're
output,
pulling out?
yeah,
Fluid in an abdomen, perhaps?
intake and output, all
Okay,
that stuff.
sure.
So you're advising them to quit drinking 2 liters of sugar soda a day?
Very appropriate comment to make, considering my soda intake today. Not quite 2 liters.
Wow.
It is going to be more common for you to deal with smaller volumes, but I will admit that it is not an exception. So here we go. 10 deciliters, 1,000 milliliters. Conversions between these units of volume, the ability to do so relatively quickly is going to be important down the line. The ability to do so accurately mathematically in this class is going to be important, but not with nearly a degree of quickness being necessary. How big is a milliliter? My daughter, last night at dinner, was telling me that at school, she had this really nifty little lesson in science class where they learned about volumes and what things would float and how you could measure the amount of an object by how much water it displaced. And they had different objects, and they took a survey of the class about, do you think this cube of wood is going to float? Do you think this cube of steel is going to float? And she got a kick out of the fact that, hey, you know what, honey? Tomorrow, when I talk to a bunch of college kids, we're going to be talking about that exact same thing. She had a very detectable air of superiority that she was learning, and she was only in 4th grade. I did not dissuade her of that air of superiority. You want to encourage learning about science. We're not going to spend a lot of time on density, buoyancy, but it's a neat thing. Okay. Here's the thing, and this gets into that rabbit hole that you brought up earlier, our exact equivalencies. How do you define? We have these standard units of measurement, right? How do you define what a milliliter is? Because it's arbitrary.
It's agreed upon reference point.
Yes, it is an agreed upon reference point, which is necessary. Our definition of everything is, for the most part, arbitrary, an agreed upon reference point. The important thing that the metric and SI systems get better than the English system is that the English system was an agreed upon reference point of whoever was in charge agreed upon reference point. The metric and SI systems have reference points that are natural, verifiable, and repeatable, instead of the length of the king's forearm, or other such things.
And yet they keep changing it.
Sort of. They keep changing it in an effort to become more and more accurate. Yes. But that would get me on a completely different rant, which I can have in our next break, about degrees of wrongness. I'll try and hold my rants for breaks so that people who don't care can leave and stretch your legs, and those who don't want to stretch their legs can just be subjected to my rant. We define a milliliter as 1 cubic centimeter of water at sea level under 1 atmosphere of pressure. All of those terms will be important at some point during the semester. But that is how we define it. Naturally occurring, measurable states. That is what a milliliter is. So 1,000 of those defines a liter. And there's some promiscuity, if you'll forgive the use of the term, in how we define these things. Because guess what our definition of 1 degree Celsius is going to involve? The ability to change the overall heat of, care to guess?
1 cc of water,
1
1
cc
degree.
of water at sea level under 1 atmosphere of pressure. Which is completely arbitrary to the amount of pressure on Earth's atmosphere. Convenient then that we currently only live on 1 planet. Martians would call that, what would you even call that, planetist? Like, if we move to Martians, would we start arguing about whose pressure we start using as our SI pressure? Or would it be entirely dependent upon how many, would we need enough people on Mars that they could, I don't know.
Sounds like you're agreeing on which language we should be using.
Oh my goodness. What a rabbit hole. Volume. 3-dimensional representation of space. 1 cubic centimeter is 1 milliliter. The volume of 1 mil is 1 cubic centimeter, no matter what shape it occupies. But the point is, it could occupy 1 cubic centimeter at sea level under 1 atmosphere of pressure. This is why you may be familiar with the term cc. 1 cubic centimeter is 1 cc is 1 mil. These are equivalencies. You could be asked about volume in any of these terms. You should be able to interchange volumes to any of those terms. Are you confident that you could do so? Hopefully you will be. Mass works the same way. 1 kilogram is 1,000 grams. That is an equivalency. 1 gram is 1,000... What's the little m stand for? Milligrams. Here's a quick cheat. It's going to be important later. When we start talking about concentration of substances in terms of molarity. Molarity is the amount of atoms of a substance. You don't have to write this down because we're going to get to it later, but I'm just telling you this so that you can understand the terms. The amount of atoms of a substance per unit volume. That's where we get Avogadro's number, and we get to also have all sorts of fun with that later. But it's not important right now. The difference is, if I tell you that a certain amount of something is 10 grams per liter, can you tell me without even thinking how many milligrams it has per milliliter? What's 1,000 divided by 1,000? 1. So if it's 10 grams per 1 liter, then how many milligrams would there be in a milliliter? 10. Because what did I have to do to take liter and turn it into milliliter? What did I divide by? 1,000. So what do you have to do to take grams and turn it into milligrams? What do you divide by? 1,000. So that means that the concentration of 10, what happens to that number? Stays the same. 10 grams per liter is exactly the same concentration as 10 milligrams per milliliter. So how many decagrams per deciliter would it be? 10. How many kilograms per kiloliter would it be? 10. Now, if I started saying how many grams per milliliter, now we're talking about math. But if I change the prefix in both the numerator and denominator, then the number doesn't change. X milligrams per milliliter is the same as X grams per liter, is the same as X kilograms per kiloliter. All right, let's learn how to write some conversion factors. This brings us back to equalities, right? What can we do with these equalities? 1 meter equals 1,000 millimeters. So what can we do with those things, which is a little bit of algebra? We can divide, right? So 1 meter divided by 1,000 millimeters is equal to 1. Can I do the other way too? What if I divide by 1 meter? Is it still just 1? If I divide this side and this side by 1 meter, then instead of getting 1,000 millimeters over a meter, let's do, see, I'm getting a little ahead of the slides because we're going to get there. But I want to get there with us figuring it out instead of it being handed to us. We all okay with that? All right. So, 1 meter, right? Excuse me. 1 meter is equal to 1,000 millimeters. So, I can divide this by 1,000 millimeters. And that means that that is now equal to what? 1.
Your denominator, yeah.
Sorry, good catch. So, here's the thing. What if I did that in the opposite direction? What does that equal to? 1. Which means 1 meter per 1,000 millimeters. That's how I would read that, right? Have you all read that before? 3 out of 4, 3 per 4 is the same thing as 3/4, right? Per equals divided by. So that means that 1 meter per 1,000 millimeters is the same as 1,000 millimeters per 1 meter. How do I know that? They're exact numbers, and we can prove it. If we did that whole cross multiplication divide thing, we can cancel these two things out. We can cancel these two things out, and what are we left with? 1 is equal to 1. Is that true? Yes. So, this is how you write equivalencies. It doesn't matter what they are. If they are stated equivalencies, you can write them like this. You can write them as fractions, and you can write them either way. You can put the meter on top or the meter on the bottom. You can put the pound on top of 16 ounces, 1 pound over 16 ounces. Or you can put 16 ounces over 1 pound. Because it's always equal to what? 1. And any number times 1 is 1. Or, excuse me, itself. Any number times 1 is itself. 1 times 1 is 1. 10 times 1 is 10. 2.49587 times 1 is whatever. The numbers in an equality between two metric units or between two SI or US system of units are definitions, which means they are exact. That's because even though the US system of measurement began as the English system, which began as arbitrary units, in order to join an international coalition of scientists, guess what we had to do? standardize our arbitrary systems as equivalencies to metric systems. Why we didn't just start using a metric system is political. So probably best avoided in this class. But
They're freedom units. Somebody labeled them as that.
like freedom fries.
Yes.
Over in France, freedom fries. 1 foot, 12 inches, 1 minute, 60 seconds, 1 gram, 100 milligrams. 454 grams is 1 pound. When we're comparing between a metric and a US system, one of those numbers is obtained by measurements and therefore counts towards significant figures. Because we had to define what a pound was. But we didn't have an exact definition of a pound. We can't say that a pound is the weight of a certain amount of water. Because guess how we define what a gram is? Can you guess? The weight of 1 cubic centimeter of water at sea level under 1 atmosphere of pressure. So if we're talking about going between a US system and the metric system, suddenly the number of significant figures matters. With one exception, and that's the one that I told you it would be handy for you to memorize earlier. 1 inch is exactly 2.54 centimeters. Because I guess we got lucky? Or maybe we just fudged what a foot was. This is why, when we do chemistry, as much as possible, unless it's a question about whether or not you understand the difference in significant figures, we're going to stick with SI or metric. Because those are exact. Equivalencies there are exact. But if we go between a pound and a gram, now we got to start worrying about significant figures in our equivalencies, and that's just going to get hairy. So here's what I mean by it's going to be handed to us, and I wanted to get there before it was handed to us. The numerator and denominator, we can switch it up. 1 hour is equal to 60 minutes, so we can have 60 minutes is 1 hour, or 1 hour is 60 minutes. It's both true, right? There are 60 minutes in an hour. There is an hour in 60 minutes. Those are both true statements, right? Why am I spending so much time on this? Because conversions are a fundamental skill. You have to be able to do these. If you don't do them right, that's when you start submitting things about a dead cow that's 2,000 pounds. Because you f***ed it up. Because you failed to apply a fundamental skill. Common inequalities. Half, if not more, of these things you've already seen in this chapter. Thrown up on one slide or another. Here's the thing about tables. You can write this stuff down if you want. Not that I'm saying a lot of you write it all down, but I'm just telling you. You can write it all down, or you can just make a mental note, or maybe note in your notes. There's a table on either this slide or that page in your book, right? Because instead of looking up slide 5 for these equivalencies, and 12 for those equivalencies, and 32 for those equivalencies, you could just go to slide, which number is this?
52.
52. Thank you. Just a little ahead of me. It's right there. It's just really small. It's got them all. Okay, caveat. It's got all of the common ones. There are an infinite number of equivalencies. You can't put them all on the table. One quart is equal to 2 pints. 1 gallon is 4 quarts. Same thing, equivalencies. 1 meter is 100 centimeters, write it either way. Metric to US, 1 kilogram is 2.2 pounds. You can write it either way, even though we do have to worry about significant figures in the lower conversion, and we don't in the top one. Right? Why? Because if we're going from metric to US, we have to worry about significant figures, with that one exception. A car travels at 85 kilometers per hour. Otherwise known as a velocity, right? Distance over time. That's velocity. A car travels at 85 miles per hour. That is an equivalency. 85 kilometers in over 1 hour. We can then use that equivalency to find out how far it travels in 2.5 hours. Or how long it would take to go 32 kilometers. Could you answer either of those questions? It's pretty simple math, right? You can also do something that's a lot more meaningful for someone in the health field. Even though it's entirely arbitrary, 1 tablet of a specific drug from a specific distributor has 500 milligrams of vitamin C. We can make an equivalency of that right here. So if you were given a prescription or told that a specific patient needed to get 750 milligrams per day, could you figure that out? How many tablets would that be? 1.5, which would be inconvenient. But if you needed 1,000, that'd be exact, right? Hand them 2 tablets and 2 baseballs, and then tell them a nifty story about your first day in Chemistry 109. Percents. Conversion factor between the amount and the unit that it is a ratio of. What? Okay, so 18% body fat by mass. If you haven't read the slide yet, because if you have, you've cheated. But if you haven't read the slide yet, how could you put that in layman's terms? If something is 18% body fat by mass, then what does that mean?
I hate them.
At 18, well actually that'd probably be better than me too. I'm probably more than 18%. I think my best was when I was in 7th grade, I was at 6.7% body fat. I was also a beanpole. I was also shortly before I started working at Wendy's, and I'm pretty sure it's just a linear downhill from there. Or would that be uphill? Because the number would be increasing? I'm not sure. Little blip, early grad school when I was running 3 miles a day. Then I met my wife. Then it just started right back up again. That's what happens in long-term relationships. It's an unfortunate reality. Anyway, that's just my story. We don't need to worry about that. So 18 kilograms of body fat, what's that mean? 18% body fat. It means for every 100 kilograms of weight, right, of mass, how much of it is fat? 18. So that's how we get 18 kilograms of body fat per 100 kilograms of body mass. Here's a common thing that happens in my biochemistry lab. You need to make a 4% sugar solution. Tell me how. With no more knowledge than what we have on this slide or what you may have brought with you into this room, tell me how to make a 4% sugar solution. Anybody? What if I said body fat? How about this? Tell me how to make an 18% sugar solution. 18 grams of sugar per how many grams of water? 100. Congratulations. You now know how to make percent solutions. Easy peasy. You could go to work in the biochem lab right now. Might require a few other skills than that, but still. That's a basic one. Why do we care? Because these conversions are going to be very important for doing math here in a little bit. One capsule, 250 milligrams of a drug. It can be worked either way, once again, for the same thing. If you want to give someone, if someone has a prescription, if they have a certain dosage, how much should they get? If it's in pill form, you can use those conversions. Most of the time, you're going to be doing this math in your head. You already know how to do this math in your head. The problem is that turning it from in your head to on paper so that you actually understand what you're doing is like asking the centipede how it walks. Do we all know that story? I don't even know what culture it comes from. How does a centipede walk? It's got 100 legs. No, it doesn't. Just go with me. It has 100 legs. How does it walk? We have a hard enough time figuring out how to walk with 2. How do you walk? It's like, well, I put my left foot forward, and then I somehow don't fall down while I lift up my right leg and put it forward, and then I just repeat that process. That's hard enough to conceptualize because it's easy to say, but think about how you actually do it. Now, how does a centipede do it? And the point of the metaphor is the centipede doesn't think about it either until you ask him how, and then he f***s it up. He can't do it anymore because he's thinking about how he does it. I don't know, and now he can't walk because he's trying too hard. You can do this math in your head, but if I asked you to do it on paper, some of you might go, oh, I don't know how to do that. Yes, you do. Do it every day. We just got to figure out how you're doing it. And then you're golden. .6. Learning goal. Use those conversion factors that we just spent so much time harping about to change from one unit to another. Core chemistry skill. Step number 1, identify the given unit and the needed unit. Write a plan that converts them between the two. In order to do that, you will have to identify one or more conversion factors that cancels units you don't need and leaves you with the units that you do. Seems simple, right? And then, last step, do that. Set it up and do it. If a person weighs 178 pounds, first off, let's finish the question. If a person weighs 178 pounds, what's the body mass in kilograms? First off, what is the unit that we are given? Pounds. Is this a SI or metric unit? Pound is English. So,
Page 52.
Yeah. Pound to kilogram. We are given pound. Find it and tell me if I'm wrong. We're given pound. What do we need? Kilogram. Okay. How do we do that? We are given pounds. We need kilograms. So what conversion factor do we need?
2.20.
Kilograms to pounds, right? Or do we need pounds to kilograms? Let's find out. So pounds, we need the US to the metric conversion factor of kilograms. We looked it up already. What is it?
I have 2.20 pounds to 1 kilogram.
2.20 pounds equals 1 kilogram. There are two ways to represent that, right? 2.20 pounds per 1 kilogram, or 1 kilogram per 2.20 pounds, right? Which one of those do we need? we need this. But only one of these two are going to give us the answer that we want. Let's find out which one. We are given 178 pounds, right? Can you guys see this over here? Do I need to, maybe? All right, so we're given 178 pounds. If I multiply that times 2.20 pounds per kilogram, what's that answer going to be? Yeah, we're going to end up with pounds squared over kilograms. Is that useful in any way? No. Now, does everyone understand why we would get pounds squared? Anybody like it? What if I change this to x and change kilograms to y? Does that look a little bit more familiar to you in algebra? What would that give you? It would give you x squared over y. Some number times x squared, right? And if we're, that's, you can't, at least here, we can't have an answer with x and y in it, like, with both of those terms, right? We need one term. We want kilograms, which in this case would be y. So, let's put that back to pounds and kilograms. So what should we do? If this one doesn't work, what about the other one? 1 kilogram over 2.20 pounds. Now what happens? Pounds above, pounds here. Let's actually work this out so you can see what I just did, shall we? Let's leave those pounds there, right? So, multiply this out on the numerator, because this is now, if we want to make it easy for math, we can just put it all over 1, right? So that we understand numerator versus denominator in fractions. If we multiply this out, what do we get? 178 pounds times kilograms, right? All right, that's on the top. What do we get on the bottom? 2.20 pounds. Well, what can we do with this? If this was x and y, if you had x, y over x, that's what?
Usually 80 point something.
Right, so we just get rid of these pounds, right? And that means that we have 178, I'm like leaning back, here, let's go down here. 178 over 2.20 kilograms. You can do this math, right? Your calculator can do this math. Let's see if we did it right. Here's our conversion, written in either form, right? Did we did it right? Kilograms over pounds? Kilograms over pounds? Good? Now, here's the thing. 178, how many significant figures it told you if you've looked? If you're cheating. Not really, it's just there. But did you know that before it told you? 3 numbers, none of them zeros, none of them placeholders, so all 3, right? So 3. 1 kilogram only has 1 significant figure, right? It's an exact number because it's a metric or SI unit. So it doesn't matter. So there's the trick question part. But this, remember, this is a kilogram to US, so 3 significant figures here. So how many significant figures should we have in our answer? 3. If this had been only 2, if it had been 2.2 pounds, then how many significant figures would we have in our answer? Just 2, right? But because the conversion factor has 3 significant figures, then that's what we can use. So the answer is 80.9 kilograms. You probably could have done that in your head. All I forced you to do was write this out, right? I'm trying to bring up something else, but I was like, no, we'll get to it. Question?
Cheryl wanted us to put those together almost like quantities. Is it necessary or does it add clarity
What do you mean? I'm not following.
to put parentheses around the first fraction in the conversion? and then around the next faction.
Oh, like this?
Yeah, because she was having to string a whole bunch of
Well, you
conversions.
can, I put the dot. Theoretically, that is redundant in so you could just put parentheses around both,
But
and
is
that
there
means it's multiplied.
any advantage to maybe getting your work
Clarity.
right? Okay.
If you are writing clearly and fully separating all of your equivalencies, no. By forcing you to put each equivalency in parentheticals, it gives you a very clear delineation between each unit, and therefore would make something like this a much more clear thing to do, right? But the only reason that it would get sloppy is if you were writing everything on, so what you could do is 178 pounds times kilograms over 1 times 2.20 pounds. You could write it all out like that. That's still just as legitimate, but I could easily see how somebody could look at that and miss something that they wrote out, or miss a number, or miss a little dot and get the wrong number because they just had sloppy math. I can see why you'd say put everything in individual parentheticals, because it forces you to think about each one individually so that you can see each one as its own contribution instead of trying to just throw the whole equation together like you just verbally splooged something. But all that is like, don't touch the stove, it's hot. I hate rules like that, but you gotta have rules like that. Until you're old enough to learn whether the stove is actually hot without touching it. And then, like my 9-year-old, we're letting her cook mac and cheese. And by cook, I mean we let her pour the pasta into the already boiling water. And stir in the butter. We don't let her actually touch the stove yet. She probably could learn, but she's also a wuss, and if she ever burned herself, she'd be screaming for hours, so it's just not worth the effort. Like, we'll let her get a couple more years on it. So whichever way is you guys need, right? Here's the thing. This was going from one unit to another unit where we had a very clear single conversion factor. That's easy. What if you needed to convert between something that didn't have one clear conversion factor? For example, what if I wanted to know how many cups there were in 1 liter? Is that an easy one? I don't want to here. I'm going to do this slow. Is that on that table? I could do this fast and put somebody in an epileptic seizure. A quart gives us a number of cups. We have a quart to mils, or quart to liters. So we have a liter to quart conversion. We have a quart to cup conversion. Could you tell me how many cups are in a liter? Sure. But you'd have to do this, you'd have to throw on a third thing here, right? Here's the number I gave you, 1 liter over 1, right? Here would be your liter to quart conversion, and then you'd have a third one right here that would be your quart to cup conversion. And you just make sure that the quarts and cups all cancel out, and so that the only thing you're left with is cups. Or liters and quarts, I guess, that you're left with cups. Everybody follow? You could do this 3 times, 5 times, 12 times. And every time you do it, if it's exact, it doesn't matter for your significant figures. But if we have anything on this table with that one exception, suddenly significant figures matter, right? So, where were we? We were somewhere in here? Yes. So given unit, in this case liters, factor 1, liters to quarts, factor 2, quarts to cups. Now you know how many cups. Conveniently enough, if you do that right by maintaining significant figures, you could then use that conversion in another problem without having to do it again. If I then asked you, here's a different number of liters, how many cups are there? You now have the liter to cup conversion, right? Because you just figured that out. As long as you use the appropriate number of significant figures. A doctor prescribed a dosage of 150 milligrams, 0.15 milligrams. That's the big difference I just made. That's the big mistake right there. 0.15 milligrams of this drug, Synthroid. You only have a 50 microgram tablet. By the way, this is something I recently learned when I went through this book specifically to teach this to nursing students. I didn't know, it mentions it somewhere in the slides as well, I didn't know that microgram in health and therefore hospital terminology is abbreviated MCG, and that's because the mu, you know what I'm saying when I say mu, the mu, let's just wave that around for a while. If you only have 50 microgram tablets in stock, how many of them do you need to get that dosage? 150 milligrams, 0.15 milligram, did it again, 0.15 milligram, you have 50 microgram tablets. How many would that take? Step back on that table, right? Where do you get this? It's not given on any table in this. For maybe a little less than half hour. Density is the comparison of an object, the mass of an object to its volume. What makes something dense? Density is the amount of an object per unit space. So something is very dense if there's a lot of that object in a very small space. What's the densest thing that you can think of? Without asking for any specific numbers, just generalities. What is the densest thing that you are aware of? Brownie points if you can think of the same thing I am, and I'll give you a hint, I'm thinking really, really small, big at the same time.
Everybody pops to gold, but they're super heavies.
Gold is fairly, yeah, it's pretty dense. It's not thick. Dense. And here's the thing, have you ever picked something up and had that like type of reaction, whereas like I did not anticipate this being that heavy, right?
Dead
Like,
weight.
that, yes, exactly. It's like the amazing, especially as a nurse, I imagine, but still, even having a parent with children, it's one of those like when a child wants to, somehow they can increase their density fourfold. Yeah, just like all they got to do is stop trying to help, and somehow they're like 4 times heavier than they normally are. Like I don't know how they do that. It's some sort of superpower they lose around the age of 8. Or at least lose the ability to intentionally, like, call upon. I don't know.
Lower center of gravity.
Neutron stars.
Oh.
See, that's cheating. Really small, really big. The density of a supermassive star is something smaller than Mercury. Where a thimbleful of mass, if you could get to a neutron star, you couldn't. If you could stand on a neutron star, you couldn't. If you could scrape off a thimbleful of a neutron star, it would weigh tons. But that's cheating. You could get even spiffier and say, well, what about black holes? And I'll tell you, you can't divide by 0, so suck it. So that's cheating. But density. Closely packed things together. Lower density things contain things that are further apart. So, metals like gold, lead, steel, they are closely packed together. There's a lot of stuff there. So they are very dense. And one of the ways that we measure density is compared to, say, water. Why does an object sink in water? Why does it float? This is in terms of buoyancy. But buoyancy is directly related to Density. Why does something sink in water?
Higher density.
It's higher density than water. Anybody have, I got this neat thermometer as a Christmas present. It's like in a corner of my living room and I never look at it. But it was a neat gift. One of those thermometers that you can put on your porch and it's got a bunch of those little like floating things in it. Different color things. It's a water thermometer, right? And how do you tell what temperature it is? Well, it's the thing that's floating. That's the temperature. How does that work? Do you have a clue? It's density related. It's different containers full of different liquids that have slightly different densities at different temperatures. So when do they start floating? When they reach a temperature where their density is equal or less than water, and then they float. If the temperature gets a little bit cooler, their density increases and suddenly it drops below water. And what happens to something with a density that is greater than water? In water, it sinks. Here's a nifty thing. Metals, like aluminum, sinks if you ball it up and get rid of the air. But if you don't ball it up, don't get rid of the air, it floats. Why?
Air is less dense than water.
Air is much less dense than water. Gas is much less dense than water. Block of steel sinks. Everybody knows that, right? So how does an aircraft carrier float? It's made of steel. Colleges in the area compete to make concrete canoes. And then they race them. It's a canoe made of concrete. Yeah, well, it's not solid concrete. If it was solid concrete, what would it do? It would sink. It's a concrete canoe. Canoes have a lot of empty space.